Hey everyone, welcome to the Drive Podcast. I'm your host, Peter Attia. Jim, so great to be with you again. We were just talking a minute ago that I had forgotten briefly that we were together once in 2013, but in many ways, this is a pretty wonderful opportunity for me to sit down with someone whose work I've been following for literally 15 years. It was May. I still remember it was May of 2011 when Tom Dayspring introduced me to your work, and I began voraciously consuming everything you had written in my personal obsession to better understand the fields of lipidology. Again, I think there can't be that many people listening to us that haven't at some point probably had an LDL-P or HDL-P test done, and yet most of them will never realize until now, presumably, that that test goes all the way back to you, and you are the creator of that. So maybe give us a little bit of a story, your journey. You did a Ph.D. in physical chemistry or
in chemistry,
okay,
and biochemistry. I was in academia for 20 years doing the kinds of things that people did in academia and do in academia using NMR spectroscopy as a structural tool. So NMR is a very common structural tool. You can find NMR machines in every chemistry department in the country. And so I had appointments in chemistry at the University of Wisconsin-Milwaukee, and then moved in 1990 to North Carolina State University. So I was basically doing my thing, minding my own business, using NMR for the usual purposes.
And for the listener, we are going to explain how NMR works, because for people who didn't take, chemistry and might not remember it, we'll come back to it. But I don't want to interrupt now to do that. Yeah, we'll come back.
Yeah, I'm not sure that that's terribly relevant, but we can talk about it. But anyway, the point is that NMR was and is very useful for a particular purpose, which is helping organic chemists determine the structure of molecules that they synthesize, for example. And I was using it to study biomolecules, so it was more challenging than small organic molecules, and trying to get at understanding what was going on at the active site of zinc metalloenzymes. But anyway, and so I was funded to do that, and had an NMR machine in Milwaukee to do that research. And then in 1986, there was a paper published in the New England Journal with a lot of hoopla, and in particular in the NMR field. People paid attention to this. I didn't normally read the New England Journal of Medicine ever, but it claimed that a very simple NMR test could tell whether somebody had cancer or not, plus or minus, irrespective of whether it was this cancer or that cancer. Nothing really in the paper that laid a mechanistic foundation for why this relationship should be. It simply measured a couple prominent signals in the NMR spectrum of blood plasma and measured how wide the signal was halfway up the signal. If it was narrow, you had cancer. If it was not narrow, you didn't have cancer. And normally this wouldn't be given much attention, but it was published in the New England Journal.
Yeah.
And so everybody who had NMR machines was interested in seeing if they could replicate this. I was in a chemistry department not associated with a medical school, so I had no idea how to get my hands on plasma if I wanted to play around with this. But I went across the street to a hospital and talked the people in the lab to giving me 6 leftover plasma samples from healthy people, and popped it into my NMR machine. And sure enough, half of the signals were narrow and half were broad. Did half of these people have cancer? No, these 3 people were women who had just given birth. So pregnancy was one false positive that was given in New England Journal paper. So that, if it wasn't for that sort of linkage to something that seemed consistent with what was published, I probably never would have taken another spectrum of plasma. But just out of scientific curiosity, we started measuring plasma and noticed that the signal that was this supposed cancer diagnostic didn't look like a nice symmetrical NMR signal. It had lumps and bumps and shoulders, and so what was up with that? And pretty quickly, when we started to ask, well, where does the signal show up, and what are the molecules that are giving rise to these signals? It was clear that these were signals from the lipids and lipoprotein particles. And so we then very serendipitously got funding from Siemens Medical Systems, basically $100,000 after me giving a 1-hour presentation for what I might learn with $100,000. So that was a pretty cool opportunity for a professor who had to go through a lot more hoops to get funding. So we had the wherewithal to get samples from people with and without cancer, and then separate the major lipoproteins, VLDL, LDL, and HDL. And we looked at those signals and noticed that the VLDL signals were always to the left of the LDL signals. The LDL signals were always to the left of the HDL signals. And it was the superposition of these signals and their relative concentrations differing that gave rise to the different shapes of this composite mixture signal that you would see in a plasma sample. So it was obvious that this signal was coming from lipoproteins. So what's up with the narrow signal, meaning cancer? Well, that turns out to be due to the fact that those signals from those people were from people with higher triglycerides and lower HDL cholesterol. And the combination of those two things made the signal narrower. So this was nothing to do with cancer per se. It was to do with the lipoproteins, the lipid levels of people with cancer. 20 years before that, people had published that people with cancer on the average have higher triglycerides and lower HDL cholesterol. So anyway, we published in 1990 or 91 a paper in clinical chemistry that showed that the NMR signals from isolated VLDL, LDL, and HDL from people with and without cancer didn't differ at all. So there was nothing distinct about whether the sample came from a cancer patient or not. But what was very reproducible, and we didn't understand why, was this phenomenology of the VLDL signals not showing up in exactly the same place as the LDL signals or the HDL signals. So we got the brilliant idea, which I didn't think was very brilliant. I thought it was obvious to use this putative cancer signal as a source of information about the concentrations of lipoproteins in the blood. So with a fairly simple, low-tech NMR spectrum that anybody could do with any NMR machine, you could generate this signal whose shape and amplitude could be used to deduce the concentrations of the VLDL, LDL, and HDL that were giving rise to that composite signal, okay? And so we had been funded by Siemens, and we published a paper in I think 1991 saying that yes, it was feasible that one could get VLDL, LDL, and HDL simultaneously from this simple NMR spectrum. So that seemed to have some advantage over the usual way of measuring triglycerides and LDL and HDL cholesterol via normal chemical methods. So so that's as far as we thought we could go. And if it wasn't for the fact that Siemens people were advising me that I never would have filed for a patent on how to do this, what did I know about patenting and what did I care about commercialization? But I did file a patent, and the patent was issued. And so if this seemed to be something useful and clinically useful, then it would have to be clinically translated, and that would have to be via some sort of commercial entity, because there were no NMR machines in clinical laboratories. In fact, there are no NMR machines to this day in clinical laboratories. So, we needed to figure out how to transition NMR spectroscopy into clinical laboratory medicine, and we needed a commercial vehicle to do that. So that was an idea that evolved over the early 1990s to about 1995, 96. Had a couple NIH grants to support the analytical development. And what we didn't expect to be able to do, but found that we could, was not only to differentiate VLDL, LDL, and HDL, but the different size subspecies that make up what we call total VLDL, total LDL, total HDL, smaller, medium-sized, larger particles. And because these signal positions are so close to each other, it just didn't seem feasible that you'd be able to work backwards from the composite signal and accurately get the concentrations of the subspecies. But we knew, by that time, I'd been reading the literature a bit, and Ron Krauss at UC Berkeley at Donner Laboratory was showing that via a quite laborious separation method, gradient gel electrophoresis and others, that you could differentiate LDL on the basis of size, and found that people with a prevalence of small, dense LDL had greater cardiovascular risk at a given LDL cholesterol level than somebody with large LDL. So this was something that was very interesting and had been replicated in literature, and people were talking about, and yet it took a couple days from start to finish to do this electrophoresis and get the result. So it wasn't really clinically translatable and efficient. And so just to see if NMR could do this, I hooked up with Ron. He sent me about 45 samples along with the gradient gel electrophoresis tracing, so I could see who had pattern A, the large LDL, pattern B, the small LDL. And sure enough, when we applied our analysis for decomposing the composite signal into its parts, we could definitely tell the difference between large and small LDL. So, okay, now we spent a couple years seeing if we could refine the methodology for quantifying small LDL, large LDL, small HDL, large HDL. And that was quite successful. So it really was with this idea that there was something really clinically useful about being able to differentiate the size of LDL particles that drove us to take the step that I was very unqualified to take, which is commercialization of NMR testing technology. It really did seem that, yes, you not only could generate the same information as a lipid panel by NMR, but really what would drive the utility of NMR testing was if it could measure something better and different. And so if we could measure small dense LDL pattern A and B, threefold greater risk associated with that at a given level of LDL cholesterol, well, that would be a pretty useful thing clinically.
Tell us how, we don't have to go into great detail, but tell us how a plasma, so you go to the doctor, they draw your blood. The last thing the patient sees is that tube of dark blood that's leaving them. Tell me what has to happen from there until they get a basic lipid panel back, which says total cholesterol is this many milligrams per deciliter, LDL cholesterol, HDL cholesterol, triglycerides, all in milligrams per deciliter. How do they get that out of that tube? What is the basic chemistry?
How do they do that chemically?
How do they do that? Yes, chemically. and in a clinical laboratory.
These are standard chemistry-based assays that are like all such assays. You add a reagent that reacts with what you're trying to measure, like triglycerides. Actually, triglycerides is interesting because triglycerides are a fatty acid esterified to glycerol. So what actually happens in that assay is the blood is exposed to a lipase that hydrolyzes, that separates the fatty acid from the glycerol. It leaves the glycerol, and then the glycerol is what something else is added to make a color change in proportion to the amount of glycerol. So this is
you're
how
actually counting the glycerol,
you're counting
and
the glycerol.
imputing how much triglyceride you had because you know it was a 3-to-1 ratio.
Yes. The clinical issue, it's not common, but there are situations where somebody has a lot of glycerol not esterified. And so the standard assays for triglyceride would say that this person has very high triglycerides, and they actually don't have high triglycerides. Anyway, so the same thing with cholesterol. So you're adding chemicals, adding reagents that cause a color change or a change in the UV spectrum that is monitored, and you have a standard curve that relates known amounts of LDL cholesterol to the signal, to the color that's created, and you can work backwards from that
So these
measurement.
can be completely automated. You're
It's
using
totally
potentially optical density or something like that,
that's
shine a
right.
light through it, and away
That's
you
right.
go.
UV detection or visible light detection. So these are really standard, very, very efficient auto analyzers do this. The challenge with cholesterol, though, so HDL cholesterol. So the problem is you're measuring the cholesterol inside VLDL, LDL, and HDL.
So when does that get broken? When do the lipoproteins break open? In what part of the assay so that you are just looking at the total amount of cholesterol contained?
Right. So the original interest in cholesterol and its relationship to cardiovascular disease risk was just total cholesterol. So basically, the reagents find all the cholesterol inside all these particles, don't differentiate where it's coming from. If you want LDL cholesterol, you have to separate the LDL particles. These are spherical containers that contain the cholesterol, and separate it from the HDL containers and the VLDL containers, and then do a regular cholesterol assay on what you've separated. So there's a separation step. Same thing for HDL. And for many years, until fairly recently, HDL cholesterol was always measured by first getting rid of the VLDL and LDL by precipitation, and then it left HDL that you then did a cholesterol assay. LDL cholesterol is more tricky because you would have to separate VLDL from LDL. And that takes an ultracentrifuge step, which is laborious, and even clinical laboratories today don't even have ultracentrifuges. Um, so, um, people devised a way of calculating LDL cholesterol by measuring, um, total cholesterol minus HDL cholesterol, which is VLDL plus LDL cholesterol, and then estimating VLDL cholesterol by dividing triglyceride by 5. Triglycerides are mostly in VLDL. So it was a an easy but not terribly accurate way of quantifying or estimating VLDL cholesterol from which you could subtract the HDL cholesterol from total cholesterol and get LDL cholesterol.
Is it safe to say, Jim, that when a patient gets a lipid panel today, unless it says LDL direct, which we'll talk about, and it just says LDL cholesterol equals 127 milligrams per deciliter, is it a safe assumption that it may have been done using that exact same methodology you described?
Yes, absolutely. And the only thing that's changed fairly recently is recognition that dividing triglyceride by 5 doesn't give a very accurate VLDL cholesterol estimate, and that impacts the accuracy of the LDL cholesterol estimate. And so now there are equations that interrogate other things, non-HDL cholesterol, triglycerides. There's an NIH equation that I help people, develop, that is used by LabCorp and other major laboratories. Um, and so you can do better than estimating it by a Friedewald formula. But most laboratories, I think, to this day, still use the Friedewald divide by 5 to get the LDL cholesterol.
So let's talk a little bit now about NMR. So again, uh, maybe someone remembers back in an organic chemistry class that one of the problems you would receive on an exam or something was you would be shown a picture, and the picture was very much like how you were just describing your experience in the 80s and 90s, where you had along an x-axis a line, and then it would have these spikes, and they would sort of correspond. So tell us what did the x-axis correspond to, and what did the amplitude or y-axis correspond to, and of course I want you to get to the point of these are protons, but get there in your own way, of course.
Yeah, so you're exactly right. That's what the output of a normal NMR spectrum looks like, irrespective of whether you're detecting protons, hydrogen nuclei, or carbon-13 or nitrogen-15, et cetera. So on the x-axis is frequency. It's just frequency. These are signals that have different frequency, and their amplitude is proportional to how much of the molecules carrying this, the hydrogens. Let's just talk about proton hydrogen NMR. They show up in different places. They have different frequencies depending on their chemical environment, and that's why this is a useful structural tool for organic chemists. So a CH2 group next to another CH2 group, as opposed to a CH2 group and a double bond or whatever it might be, they show up in very different places, and there's other differences that are structure dependent. So you can work back from an NMR spectrum and deduce the structure of the compounds that are giving rise to that. Um, so so this was never used though as a quantitative analysis tool. It was used, so it's relative signal intensities would tell you how many protons are here in a molecule, how many protons are there on the molecule. Does that fit the structure that you were attempting to synthesize, for example?
And so just, I just want to make sure people understand what you're getting at there. So you're trying to synthesize something, you know the structure of the thing you're trying to synthesize.
You think you know it.
You think you know it, and therefore you should know what its spectra looks like. And now you're basically trying to match the
Yes.
NMR of what you've synthesized to say, look, this should have a carbon, a double bond, a carbon, a single bond. Over here is going to be an oxygen that's going to produce. And it's I mean, it's a really fun game. I mean, not to be too nerdy about it, but it's a super fun puzzle to solve effectively.
Yeah, and it's pretty complicated, and I haven't done that sort of thing in 50 years. So I moved to a different application, which is using NMR to detect a single signal. So I didn't care about what was in the rest of the spectrum. I cared about the signals that were these putative cancer signals. So from the terminal methyl groups of the fatty acid chains that are carried on different types of lipids that are carried in these lipoprotein particles.
By the way, did the NMGA, New England Journal of Medicine authors know that they were looking at lipoproteins?
I think they said lipids. I can't
Okay.
remember,
Yeah.
and again, and I think, yes, that they did. And they suggested that if you had cancer, there was some structural alteration in the lipoproteins
Got
that
it.
gave rise to a different signal. And that's what we disproved by
Yep.
showing that that wasn't true.
Yep.
Okay. So anyway, back to this issue of whether we could use that so-called cancer signal as a source of quantitative information about the lipids and lipoproteins, or the lipoproteins themselves. So what I told you is true. It was empirical observation that there was this very consistent relationship between where the frequency of the signal from the very same methyl groups on the very same molecules. So the molecules don't differ at all in terms of what's carried in VLDL, LDL, and HDL. It's the same lipids, so you'd expect they would all show up in exactly the same place. But for some magical physical chemical reason that is explained by complex equations that I don't even understand very well, it's been shown that a larger particle will always give rise to a signal that has a slightly lower frequency, and a smaller signal will have a slightly higher frequency. So the same lipids in different size packages show up in slightly different places, but very reproducibly different places. And so the idea is that if you understand exactly where the signal shows up from a particular diameter lipoprotein particle, and also measure that, because the shape of the signal will differ, that's another complexity, but adds to the accuracy of what we're able to come up with. So with a complete understanding of what the different parts are that make up the mixture, make up the whole idea is that you measure the whole and then you decompose it into the parts. So the sum of the parts equals the whole. What's efficient about the methodology is that you're measuring something with a really low-tech, simple NMR spectrum that you can obtain in 30 seconds. A computer then, with a deconvolution model that has in it what the signals look like from all the different sizes of VLDL, LDL, and HDL subclasses, and then take that measured 30-second measured composite signal and spit out how big the signals must be from all the different constituent parts. To when they superimpose, they will recreate that shape of the composite signal. Okay, so that's the idea that the concentration information comes from how big the deduced NMR signal intensities are in this mixture, blood.
Sorry, one point to just add to that, Jim, that a person who's looking at their own NMR result in their blood test will notice that the units are reported
Yes.
as nanomoles per liter as opposed to milligrams per deciliter. So it's not a mass concentration, it's a molar concentration. Maybe explain to
Yeah,
people
that's
what
just
that
where I was
distinction
going to
is.
go next,
Okay.
because as I told you, the chemical constituents in these particles, and they're quite heterogeneous. There's different size lengths of fatty acid chains. Some are saturated, some are monounsaturated, some are polyunsaturated. All of these things um, give rise to the lipid complexity of these particles. But the way the NMR detection, at least of this signal, knows nothing about any of that. It's basically a lipoprotein particle signal. And so what should be the case, if that's true, is that how big that NMR signal is from the particle should relate to the number of particles, irrespective of what the lipid concentrations are. And there are variable amounts of cholesterol and triglyceride in most lipoproteins. So what we realized at the beginning was, if this was a lipoprotein particle signal we were interrogating, we could get lipoprotein particle concentration information, but we could not and should not report lipoprotein cholesterol levels or lipoprotein triglyceride levels, because we actually weren't able to differentiate the signals from those different chemical species. So that is what we started to produce when we did this commercialization thing, which I may come back to a little bit. But as you said, what's reported, LDL-P, is the particle concentration in nanomoles per liter. So there's 6.02 times 10 to the 23rd particles in a mole of LDL. And so this is 10 to the minus ninth. Anyway, so it's a big number. It's still 10 to the 16th particles. So there's a lot of these particles in your blood. But you're reporting the concentration of the package, not the lipid molecules in the package, okay? So then the question is, or one question is there any advantage to that? I mean, because by then, so I'll go back a little bit to the commercialization, because as I said, the commercialization was driven by the idea that small dense LDL is much more atherogenic, much more to worry about than large LDL. And our own studies, when we started measuring small and large LDL by NMR and did it in large population studies, we found exactly the same thing that Ron Krauss and others did.
And which population did you look at? Did first Mesa, Framingham?
Framingham for sure back in the day. Mesa came a little bit later. But I can't remember what we initially looked at. But the point is that when looked at through the lens of, at a given quantity of LDL, if the LDL is small versus large, does it make a difference in your cardiovascular risk? When I said the concentration of the quantity of LDL, the way everybody thinks of the concentration of LDL is LDL cholesterol. And that's what Ron Krauss and that's what we did. We said, okay, at a given level of LDL cholesterol, you take people and you stratify them according to low, medium, and high LDL cholesterol, or you do a multilinear regression and put LDL cholesterol in the model, and now you're asking, does the size of the LDL add anything to LDL cholesterol in cardiovascular risk prediction? And sure enough, it does. And it's quite an impressive increment of risk. So we reproduced what Ron Krauss did. However, we realized, because we were also in the business of measuring LDL particles, that by definition, if an LDL particle is smaller versus larger, it's always full of lipid. You don't get a partially filled container of LDL. It's always full. So a smaller LDL particle means, by definition, that it's carrying less cholesterol, less lipid per particle than a large LDL particle. So the phenomenology is, at a given level of LDL cholesterol, people with small dense LDL have higher cardiovascular risk. The trouble is that people with small dense LDL at a given level of LDL cholesterol have more LDL particles. Their LDL-P is higher than would have been imagined from the LDL cholesterol measurement. So an alternate explanation for the extra risk that small dense LDL seem to confer is that there are simply more particles, rather than the size of the particles being the determining characteristic of the atherogenicity of these particles.
Yeah, let me just use a silly childlike example to make this point. So imagine you had 4 lipoproteins that each contain 3 units of cholesterol. They're fully saturated at 3 units of cholesterol. So you have 4 of them, so you have 12 units of cholesterol. Now imagine you have 3 spherical lipoproteins that each have 4 units of cholesterol. They're fully saturated, so they're obviously bigger, but they also collectively have 12 units of cholesterol. So here you have 2 people, one has 12 units of cholesterol, but it's being carried with 4 lipoproteins. The other has the same 12 units of cholesterol, carried by 3. You're telling me all the data say the first person is at higher risk. The question is, are they at higher risk because their spheres are smaller, or are they at higher risk because they have more spheres, which happen to be smaller?
Correct. So you explained that very well. And so this is basically how science works. So you have a different explanation for the phenomenology of small dense LDL having this seemingly extra atherogenicity. It's then testable. So it's quite straightforward at that point to ask the question, at a given level of LDL particles, if you stratify people according to LDL-P, and then say some people have small LDL, some people have large, is there any difference in their risk? And the answer is not a bit. And
So
we
now
did this
again,
in many
now
studies.
the example is you have 2 patients that each have 20 particles.
Yep.
One of them is 10 big, 10 small. The other one is 15 big, 5 small. If the particle size matters, the first one should be at higher risk. If the particle size is irrelevant, once you've corrected for total number, they should be at the same risk.
Right.
You're saying they're at the same risk.
That's right. And why does this matter? I mean, if you're only interested in assessing the risk of a person, you're equally well off with the cholesterol information and the size information as the particle information and the size. The particle information, the size doesn't add to that. The reason that's important is that if you believe that small LDL is bad and you can make it less bad by making the particles bigger therapeutically somehow, then you will be telling patients that at a given, let's say they get treated with statins and they lower their LDL cholesterol or their LDL particle concentration to an acceptably low level, but the particles are still small. Somebody who believes small dense LDL is particularly bad will then try to do something to make them bigger and imagine that there's clinical benefit. And a lot of drugs actually have that effect. CETP inhibitors are one of them. Niacin, HDL drugs of a different type. So triglyceride lowering automatically will have this effect. So there really are a lot of clinical trials that imagined when they set out to do the clinical trial that there would be a lot of efficacy, like niacin, for example, because not only did that modestly raise HDL cholesterol and lower triglyceride, which were 2 good things, seemingly, but it made the LDL particles bigger and it made the HDL particles bigger because there's also a similar argument about the size being important in HDL. And yet there was no efficacy when they did the outcome studies. And this has been reproduced with the fibrates and other drugs.
So, Jim, what would you say to the person listening who, because I hear this all the time, who says, hey guys, I do have a high LDL cholesterol, and even my LDL particle number is very high on my NMR test, but I'm very pattern A. You see, all of my LDL are very large, and they even use words like fluffy
Yes, they
and
do.
buoyant. I have large, fluffy, buoyant,
Benign.
yes, LDL. So my LDL particle number is over 2,000 nanomole per liter, which probably places me at the 80th percentile or so. But I don't need to worry about it because they're all big. I don't have that pattern B. I don't have that small. What would you say to that person?
I would say that's a fallacious idea. And the data that I mentioned supports it completely. And then you also have to think about the fact that one of the best known, best accepted genetic reasons for cardiovascular risk is FH, familial hypercholesterolemia. People with FH have very high LDL cholesterol levels. They also have very high LDL particle levels, but those particles are large. They're not small. And these are people that die when they're 30 or 35 years old when they're homozygous FH. So this idea that somehow fluffy, large LDL particles are not to worry about, are benign, is completely fallacious.
Let's talk about one more thing on this before we pivot away from this, which you alluded to very briefly, but we went off on a different path, which is the potential discordance that exists between LDL cholesterol and LDL particle number. And in fact, when I first came to learn about your work, Jim, this was actually one of the first papers I read of yours, literally 15 years ago, almost to the month. And it was in the MESA population, and it was showing 4 Kaplan-Meier curves. So I'll let you explain what a Kaplan-Meier curve is, but it was basically the 4 scenarios, which was discordance between LDL-P and LDL-C when one is higher than the other each time, and then concordance between them. So maybe there were 3 curves then in that.
That's exactly.
Yeah, there were 3 curves. Okay, so concordance between LDL-C and LDL-P, and discordance in favor of LDL-P, discordance in favor of okay. So that was a very, very eye-opening paper to me. And I'd love you to just kind of explain that finding and what the significance are, because to this day, it's still a very important thing for clinicians and patients to understand.
No, it is. And prior to that MESA paper in 2011 was a 2007 paper. So it was the first one that we sort of introduced this idea of assessing the situation by whether the LDL-P and the LDL-C agreed or not. And in that case, it was a Framingham study. And in that case, one question that always comes up is, well, what defines discordance? And basically, it doesn't matter, and everybody defines it differently. And it doesn't matter because we're not saying discordance is a risk factor, right? We're simply trying to disentangle a situation where most people don't have a discrepancy between LDL-C and LDL-P. So if you're trying to understand whether LDL-P is a better measure of LDL-associated cardiovascular risk, and you do a whole study population, and 80% of those people have concordant or in agreement LDL-C and LDL-P.
And just explain what that means, because people will say, well, the numbers are different. How can they be in agreement?
Okay, so one way to do it, which we did in the MESA paper, is transform the milligram per deciliter cholesterol number into a percentile. So that defines people according to their rank, low, high, intermediate. And if you do the same thing to the LDL-P, now you're comparing apples to apples, percentile of one, percentile of the other, and you plot that, and then you see the data points all over the place. And the ones that track on the diagonal, the ones that are close to the diagonal, are the ones for which a 50 percentile LDL-P is close to a 50 percentile LDL-C. So that's what we call concordance. And in that case, we picked this weird number of 12 percentile difference was our cut point, plus or minus. So everybody within 12 percentile units of each other, we called concordant. Why 12? Why not a round number? And it was because we were trying to make the concordant population about equal in number to the discordant in one direction and the discordant in other direction population.
Yeah, so you had 50% in one, 25, and 50% in the 2 discordant groups.
No, it's actually, we're trying to make it sort of 30-30,
I see, 30-30-30, got it, okay.
So that's what we did. And then we simply took these 3 groups of people, and you talk about Kaplan-Meier, all this is basically cumulative incidence of cardiovascular events. So on the x-axis, you can see the number increasing. If it increases a lot, this is a higher risk subpopulation than somebody whose risk is much shallower and doesn't increase very much as a function of concentration. So that very clearly showed that for people whose LDL-P and LDL-C agree, you can make no argument about why LDL-P is a better thing to measure than LDL-C. Then it's a matter of, well, from first principles, what would we expect the cholesterol to be a better measure of risk or the particle number? And really, if you're honest about it, there is no mechanistic explanation that you should really be too comfortable with for one versus the other. And we explained that in that paper, that what has happened with when Ron Krauss showed that small dense LDL was more atherogenic, and that this was based on epidemiologic, population studies. The question was, well, why is that? And then basically the speculation was, ultimately supported by various lines of evidence, that yes, smaller LDL particles are likely to get into the arterial wall easier than a bigger particle, and then the difference in the shape of the stuff on the surface of the particles can bind more avidly to molecules that are in the arterial wall and retain it more, and then it's more readily oxidized. So all of these things, I can't tell you how many papers I've read where in the discussion section is this obligatory paragraph about why small dense LDL is so much more atherogenic. The flip side argument is that, okay, large LDL particles also get into the artery wall. And when they get oxidized,
they're more retained.
they're not more
Well, I mean,
retained.
I'm just saying you could make that argument, right? You
Well,
could always,
let's just say that they get to the end of the trail and they get taken up by macrophages and deposit their cholesterol contents into the arterial wall. Well, bigger particles have more
more
cholesterol to
cholesterol, more
deliver.
oxidative damage.
So
Yeah.
you'd think the more cholesterol-rich particles should be more atherogenic.
Yep.
But if that's counterbalanced by not getting to the end of the party as often as the small particles, maybe it's a wash. How do you answer the question? You do the study. And so that's what the discordance analyses allowed us to do. Whenever there's a discrepancy in one direction or another, the cardiovascular risk tracks with the particle number, not the cholesterol.
Yeah, so the curve really had a beautiful separation of those three figures. You had the concordance in the middle, and then above that line, which means these are people that are dying quicker, that's when LDL-P was above LDL-C. And below the line, these people died much slower than you would expect. It was the
Their
flip.
cholesterol was high, but their particles were low.
Exactly.
Yeah. So yeah, so
I mean, and I can't tell you how many debates I had to have with people, I mean, usually very well-regarded cardiologists,
tell me about it.
who just refused to acknowledge there was ever a need to look at anything beyond LDL cholesterol.
Right. Well, now let me sort of go somewhere about the clinical utility of this, because what people would imagine from having said all this is that LDL-P should be a much better thing to use to assess cardiovascular risk. And the reality is that the way cardiovascular risk is assessed today is pretty much the same way it's always been assessed, by equations that take into account total cholesterol, HDL cholesterol, diabetes, present, absent, smoking, present, absent, hypertension. So these are risk equations, and there's updated risk equations, just fairly recently a new one. They all have total and HDL cholesterol in it. When you ask the question, if I use LDL-P or I add LDL-P to a model that has those things in it, is my risk assessment better? And the answer is no, it's not better. And this sort of kills you if you're trying to, make a commercial argument that you should be testing LDL-P instead of LDL-C for risk assessment. The reason I think that is true is because the HDL cholesterol is in the model, and we still don't really understand whether it's HDL is bringing extra risk assessment to the table above and beyond what the LDL and the total cholesterol brings. Or is it the triglyceride-rich particles? Now, people have swung away from the idea that HDL cholesterol is important because the HDL cholesterol raising trials were negative or weren't positive. And then because there's an inverse correlation between triglyceride and HDL cholesterol. When HDL cholesterol is low, triglycerides are high. Oh, maybe it's the triglycerides. Well, it doesn't make sense that the triglycerides per se, the molecules triglyceride, are atherogenic, but the triglyceride-rich particles that carry them could well be, because they also get into the arterial wall and deliver a lot of cholesterol.
Now, Jim, I don't know if this was one of your papers, but I think it was. And it was around that time, probably 2012, 2013. And if I recall the paper, the figure specifically, it was a histogram, right? So on the x-axis, you had 0, 1, 2, 3, 4, 5, and you were looking at number of criteria met for metabolic syndrome. So for the listener, just to remind everybody, metabolic syndrome has these 5 criteria, and the more of them you have, the more likely you are to be insulin resistant. So there's one about having high blood pressure, obesity, so the truncal diameter, truncal girth, blood pressure, fasting glucose, and HDL cholesterol. I think those are the 5, right?
Yes.
Doesn't include, yeah. Okay. So, and what this figure showed was if you had 0 of them, the probability that you were discordant between your LDL-C and LDL-P was very low. If you had 1 of them, the probability went up a little bit, 2 of them considerably, 3 a lot, and it was a monotonic increasing relationship, Jim, such that by the time you had 5 out of 5 met-sin criteria, you were virtually guaranteed to be discordant.
Right.
And so I bring that up to say, earlier you mentioned there's nothing wrong with being discordant per se, although you could also argue that the more discordant you are, the higher the probability that you're discordant means the higher the probability that you probably have some underlying metabolic insulin resistance.
Extra risk.
Yeah.
Yeah.
And so the question then becomes, is the reason that very elaborate multiparametric risk models can erase the LDL-P is that they are simply capturing all of the cardiometabolic risk indirectly and directly?
Yeah, you basically just explained what I was getting at, which is because HDL cholesterol is in the standard risk assessment models, when you have low HDL cholesterol, you're likely to have more LDL-P than the LDL cholesterol indicates or suggests. And so your risk is higher because you have higher LDL-P, not because HDL cholesterol is low. But you're not doing better in risk assessment because the HDL cholesterol, for the wrong reason, if you will, not a causal reason, but an association reason, is telling you the same thing. So this was really important to liposcience back in the day because, and this is something that I still argue with, but Alan Snyderman and I, we'll get to the question of apoB.
Yes, yes.
But he keeps wanting to convince people that apoB is important for risk assessment. And what we pivoted to in light of the evidence that we found ourselves, that above and beyond the standard risk equations, you couldn't add LDL-P and see a significant increase in risk. Liposcience pivoted from trying to convince people that LDL-P was a better thing to measure for risk assessment to a better thing to measure for risk management, because what you do when you have high risk is you manage it by lowering your LDL cholesterol. This is the best tool we have in the toolbox. There are not actually very many others. We have statins, and then we have things that are doing the same job as statins, but better. So we can lower the heck out of LDL. And the question for a patient with high cardiovascular risk is, how much LDL lowering do I need? And so what you really would like is a biomarker that tells you my LDL-associated risk is adequately controlled. I've gotten my LDL low enough. If it's not, I should add, if I'm on high-dose statin and I'm not there, then I want to add a PCSK9 inhibitor or something else to lower it even more. So you want the best objective measure of LDL-related risk, not total risk, but LDL-related risk. In that case, it's very clear that LDL-P or apoB is a better biomarker because a lot of people who achieve very low LDL cholesterol have not achieved equally very low LDL particles or apoB, and they therefore, with visibility to that, would be candidates for more aggressive LDL lowering.
So we absolutely notice that as clear as day in our practice, Jim, because we are very aggressive at managing these things. And is there a biologic reason for why the discordance really happens at low levels in that way? Or is it a chemical assay? Is it a property of the assays that's causing that?
No, it's like everything that you ask. It's complicated. You can get into the weeds, but what's true is that the lower your LDL level is, the more likely that the cholesterol in the LDL particle is replaced to some extent by triglyceride, because there's always this interchange, this swapping of
Hmm.
cholesterol, ester, and triglyceride in the core of the particle. And it's driven by the relative amounts of the triglyceride-rich particles and the LDL particles, which are cholesterol-rich. The triglyceride-rich particles, the bigger that gap is, put triglyceride into LDL in exchange for cholesterol ester. And so as you lower LDL with statins or whatever, the LDL particles are lower, but the LDL cholesterol is even lower because not only has the particle number gone down, but the cholesterol in the particles independently has gone
Disproportionately is
down.
going down.
Okay,
That's actually a great explanation.
good.
I did not know that, and that makes sense because we see that as clear as day.
Right.
Okay, one other thing I want to talk about on this front before we pivot is, at least to my knowledge, the first composite score that you then developed out of that, which was the LP-IR score. Was that indeed sort of your first foray into cool composite scores?
Yes, and it was
Still
because
used to this day, so many
yeah,
people,
no,
again,
it's
listening to
it's
us will have an LP-IR score every
yeah.
time they get their blood test.
No, it's interesting because, as I said, we first got into this game because we could measure small LDL and so the ability to differentiate different size lipoprotein particles seemed like it was clinically useful. But at the end of the day, as I've gone through, it turns out that it's really the particle number that matters. And if you can convince people to not pay so much attention to LDL cholesterol and pay more attention to apoB or LDL-P, uh, then you're better off. But that means that measuring the size of LDL doesn't matter. Oh, that's a bummer because we have a great efficient way of doing that. So then the question was, well, are the lipoprotein subclass distributions useful for something else besides cardiovascular risk assessment and management? And the answer is absolutely yes. There is a well-known association between higher triglycerides and lower HDL cholesterol and insulin resistance and diabetes, and insulin resistance leading to diabetes risk or leading to diabetes. So it's already known that there's a lipid signature for insulin resistance. And the idea was, if we could measure the different sizes of VLDL, LDL, and HDL, could that do a better job than just the triglyceride over HDL cholesterol ratio? So the poor man's insulin resistance measure from a lipid panel is triglyceride over HDL cholesterol ratio. And Jerry Reven, who was the really discovered and promoted the idea of insulin resistance being extremely important, he advocated that it be used because people were getting lipid panels and this information was not being used for anything. So with this LPIR score, which brews together 6 VLDL, LDL, and HDL size and subclass concentration parameters, it brews them into a score from 0 to 100, higher scores being more insulin resistant. And then the question was, does this LPIR score do a better job in assessing whether somebody is likely to become diabetic? So the pathophysiology has to be talked about a little bit here, um, because there's some interesting parallels to where we are today with respect to primary prevention of cardiovascular disease versus primary prevention of diabetes. So in the cardiovascular situation, as everybody pretty well understands, the initiating causal factor there is elevated cholesterol or elevated LDL or elevated apoB, but it's acting over time. So it requires an integration of exposure over a long period of time, and that gradually leads to cholesterol deposition in the artery wall. That's atherosclerosis. Atherosclerosis over time starts little, more, but that doesn't trigger any clinical concern. This is a subclinical manifestation of cholesterol doing its dirty deed over a long period of time. And then at some point, you might have a myocardial infarction or a stroke. And that's when the atherosclerosis has transformed into a clinical event. The good news from a measurement biomarker standpoint is that the initiator, the causal factor, is cholesterol, which is easily measured. So now what about diabetes? Diabetes, very similar. It's a time-integrated process where if you are insulin resistant, over time, your beta cells have to spit out more insulin to keep your glucose under control. And so you're making the beta cells work harder, if you want to think about it that way, if you're insulin resistant versus insulin sensitive. And so insulin resistance times time leads gradually to hyperglycemia, elevated glucose. So if it's 90 or below, you're A-OK. But over time, if you're going to convert to diabetes, you go through a transition of the glucose going higher and higher until it crosses this magic 126 milligram per deciliter line that defines diabetes.
Just for folks to know, we're talking average.
Absolutely.
Yeah.
So the causal factor is insulin resistance. The thing that's sort of equivalent to atherosclerosis on the CVD side is hyperglycemia, less than 126. So not diabetes, but pre-diabetes. So when glucose gets over 100, before it goes from 100 to 126, you're pre-diabetic. Guess what's easy to measure? Glucose. So in that case, the effect of the cause is measurable. The cause itself is not. And so what that means is that from a prevention standpoint, what you really want to do is to keep insulin resistance from transforming over time into hyperglycemia and ultimately diabetes. If you don't know that you're insulin resistant, you're waiting for the easily measured glucose to become elevated. And now, once that happens, you've lost about 50% of your beta cell function. So the opportunity for real effective prevention, primary prevention, primordial prevention, is to act on people whose glucose is okay and hasn't gone to this transition yet because the beta cells have started dysfunctioning.
So Jim, I want to pause you there
Yeah.
because the way you've laid that out is very elegant. And I like I've never thought of it the way you just explained it. So I'm repeating it just as much for me as for others. People who listen to this podcast know we constantly use the way you describe the CVD prevention thing, which is you have a causal marker. You don't need to wait until disease is measurable to treat it. And the example I always give is smoking and lung cancer. We have a causal marker, for lack of a better word, smoking. We always have to specify causality doesn't mean one-to-one mapping. There are some smokers that never get lung cancer. There are some never smokers who still get lung cancer. None of those facts erase the causality of tobacco and lung cancer. Do we need to wait for a smoker to develop a small cancer to tell them to stop smoking? Absolutely not. That would be malpractice. You always eradicate causal drivers of disease the moment they appear. And that's why when you have elevated LDL-C or apoB or LDL-P, you treat it immediately, not once they have disease. Same with hypertension, same with smoking as it pertains to cardiovascular disease. Now let's pivot to what you said, which is, look, we know that insulin resistance is the cigarette to diabetes as cancer.
Yes.
Do we want to wait until we actually see the glucose rise, which, by the way, is the biomarker that defines diabetes, when in reality, by the time that's happening, there's potentially already cellular damage at the level of the beta cell in the pancreas, and it's basically running out of steam. And what else can we measure? Now, I want to come back to the idea of there are things that we can do, but they're very laborious. So an oral glucose tolerance test is a fantastic way to find out that canary in the coal mine years before it shows up. But it's so fallen out of favor as a clinical test because it takes 2 hours. It's just so cumbersome to do that outside of our practice and a few others, I just don't imagine many people want to do it. So Jim comes along and says, what if somewhere in this NMR spectrum is a whole series of things that turn out to be a fantastic marker for insulin resistance that we can use as causal proof that you're on the wrong path before your glucose goes up?
Yes, and it seemed to us a very compelling case that you would want to act on the causal factor and not the effect or the downstream effect of the action of insulin resistance. Um, but it's interesting. I mean, back to convincing people, clinical translation. I mean, I use that word. I don't think I was familiar with that word when I started this company called Liposcience uh, to try to get NMR testing introduced into clinical laboratories. But I thought the argument of LDL-P versus LDL-C was quite compelling and that people really should be using it as the biomarker to determine management of LDL. Tremendous resistance by the establishment. I could never understand why it was so, why they were so resistant. Uh, the messaging, people learn about cholesterol in medical school. Oh, we'd have to tell a different story and people wouldn't get it, and all sorts of, reasons that seem pretty weak to me. Um, so on the diabetes side, it's the same thing. People imagine that hyperglycemia, prediabetes, is a risk factor for diabetes. It's not a risk factor. It is the disease. It's just in a less manifest form. So why not address the cause? A lot of resistance to that. It sort of blew my mind. And we did NMR analysis in a number of studies to show the efficacy of, or at least the relationship between insulin resistance score and likelihood of future diabetes. And by the way, transitioning to prediabetes by no means means that you're going to get diabetes. I mean, there's you really, my wife has been pre-diabetic, 105 or so milligram per deciliter for 25 years. Doesn't change. Um, so the insulin resistance score can tell you whether you're more or less likely, once you're pre-diabetic, to transition. And then at that point, even though you'd like to have intervened earlier, it's not too late to still do something about it.
And so, Jim, was the LP-IR score validated on longitudinal data to predict the development of type 2 diabetes?
Yes.
Or, okay. So in that sense, we'll talk about MVX and how similar that was in that regard. Has there ever been a comparison that says how well does it do versus
Yes.
an oral glucose tolerance test? Yeah.
Yes. And so, well, not oral glucose tolerance test, because in the real world,
Too
it's not being
complicated.
used. So you're really fasting insulin is sort of an easier way to assess insulin resistance. It has some analytic issues and practical issues. So nobody has really been interested in using insulin for that purpose generally in clinical practice. But the LPIR score has been compared to fasting insulin and is better. The study that shows it the best is one that unfortunately hasn't been published yet. It got very close to having the manuscript be written. It's in the diabetes prevention program, so you couldn't ask for a better study, because this was a study that put intervention, lifestyle intervention, metformin, on the map in terms of being able to do something about transitioning to diabetes once you had hyperglycemia, once you were pre-diabetic. So this study was done about 20 years ago. We have baseline samples and then 1-year samples post-treatment. Everybody in the study had an NMR analysis done. LPIR and other things that we can measure by NMR that make LPIR better if you want it to be better, were shown to be independently predictive, better than insulin. But most importantly, because that was an intervention study, lifestyle change and weight loss was shown to significantly reduce the incidence of diabetes in these people. Metformin less effective, but significant compared to placebo. So what we were able to show really nicely is that the LPIR score was reduced significantly by lifestyle, less significantly by metformin. Branched-chain amino acids, which we haven't talked about yet, but higher branched-chain amino acids are also related to insulin resistance and can improve the LPIR score. And we actually have developed another score called the Diabetes Risk Index that integrates or adds branched-chain amino acids to LP-IR.
Okay, I was going to ask you that. So just to confirm, the DRI, the Diabetes Risk Index, is the LP-IR score inclusive of the 3 branched-chain amino acids. And do you recommend when do you recommend using one of those versus the other?
Well, it really never has gotten to be far enough along or far to have the amount of acceptance um, that discussion has even occurred.
Is DRI commercially available with
It
LabCorp
is.
now?
It is at LabCorp.
Okay. We should also point out for folks who are wondering, your company, Liposcience, that you founded in mid-90s, was acquired by LabCorp 10 years ago,
Yes.
a little more than
Yes.
10 years ago.
Yes.
And so for those of us like me, the dinosaurs, like we used to still order a Liposcience test. Now it just all happens through LabCorp. So that presumably that has increased, I assume, some uptake of the test.
So I wanted at some point to get into the question of why hasn't broad clinical translation occurred? Because it hasn't. Right now, you can only go to LabCorp for this information. So I'll go there now briefly, if you don't mind.
Please.
So Liposcience began, as I told you, as a spinoff of the university. I left the university, and we tried to convince people that size didn't matter and LDL-P did matter, and we did that for quite some time. And we were a laboratory testing company, and so samples were sent to Liposcience, and you get the results back.
You had beautiful results.
And the color report.
I loved it so
Why
much.
not use color printers?
No, it was beautiful.
But the ambition was never, or the business objective was never to be a lab that got bigger and bigger and did more testing. It was to make the ability to do NMR testing available to any laboratory in the world. So, we started by what was available. I talked about NMR machines being in every chemistry department. These are research NMR machines. They're engineered for multifunctionality. You can do any weird NMR experiment. There's lots of variations on the theme. We wanted NMR to do one thing very efficiently and as rapidly as possible. And so, ideally 30 seconds or less, pop one sample in, automatically another sample comes in, boom, boom, boom. So we realized that we couldn't use a research NMR spectrometer for that purpose. We used them for the initial years at Liposcience because that's all there was. But we wanted to transition from a lab testing company into an IVD company, in vitro diagnostics company. All laboratories rely on IVD companies to supply them the machinery and the reagents to do all these assays. So LabCorp does 3,000 assays. They rely on other people, Roche, other people, to provide them with the wherewithal to do the testing. Those are IVD companies. We wanted to be an IVD company at Liposcience, make an NMR analyzer that looked just like a regular chemistry analyzer to a med tech that had no experience, no knowledge of NMR, walk up to it with 200 samples, present the tray, push the green go button, and walk away. And so that's what we actually did. And a lot of investment and a lot of time and effort was put into that. And that is the Vantera NMR analyzer. It's the only existing NMR analyzer in the world. And we went to the FDA because these analyzers have to be FDA cleared in order to go into different laboratories. That was an adventure because what did FDA know about NMR spectroscopy? And it was a new platform, a new way of testing that had to be understood. So anyway, it took
When did you get the CLIA approval?
Not CLIA. We got FDA clearance for LDL-P and the Vantera analyzer in 2011.
Oh, wow. Okay.
Yeah, 2011. And so these Vantera analyzers, a number of them were manufactured, and then we about the time that just before a year or so before Liposcience was sold to LabCorp, these analyzers were started to be distributed to major laboratories. LabCorp was one of the recipients of these analyzers, so they could do the testing in-house rather than having to send the samples to Liposcience. Clinical laboratories hate send out samples. And when that's for a rare cancer or something, when it's just a fairly rare event, no big deal. If you're doing hundreds of these a day, you don't want that hassle. So they were very happy to receive the Vantera analyzer so they could do the testing in-house. And every time they did, they would pay LipoScience for each analysis. Okay, that was the business model. We also made Vantera analyzers available to the Mayo Clinic, Cleveland Clinic, Scripps Clinic, ARUP, a big reference laboratory in Utah. So we were on the way to making it available broadly because we didn't want to be the only people that could do NMR testing.
sure.
And also we wanted to convince people that this wasn't, magic. It was real. And it was analytically, in many respects, much better than reagent-based chemistry testing. Unfortunately, by that time, LipoScience had gone public. I was no longer on the board. I was basically the investment that we needed to start LipoScience. We basically took too long to get to the payout of the initial investors. So the investors were not patient. They were very patient up until then, but you almost couldn't blame them because they wanted to get their money back, venture capital in particular. So the company went public, and then LabCorp came along and said, we'd like to buy you because we can make more money if we don't have to pay whatever number of dollars to LipoScience every time we do this test. So it was a purely financial decision. LabCorp really didn't care about measuring things other than the NMR lipoprofile, the LDL-P, et cetera. It was financially based. That was too bad for the vision of having NMR analyzers in every laboratory because LabCorp is a lab testing company. It's not an IVD company. So too bad. The IVD business model, the IVD vision was ended in 2014. So yes.
Did you join? Did you go and become a
The
scientist
research group largely was retained by LabCorp. So, and we had a pipeline of things like LP-IR and things, DRI, things that were coming down the pike that we'll talk about later. So, really the best was yet to come in terms of the clinical value and the things that could convince people that having Vantera analyzers in their lab was a commercially useful thing, but also a clinically useful thing. So the bad news is that LabCorp, understandably not sharing the IVD vision and being a laboratory that wanted to have NMR be proprietary to themselves, took back these analyzers that had been placed in these other reference laboratories. And then, unlike LipoScience, that knew that when it developed a new test, it needed to go to the trouble of creating awareness and interest and doing the studies to prove the clinical efficacy of these tests. That's a very important activity. LabCorp doesn't do that because they're not an IVD company. They are reactive. They're not proactive. They're very good at being reactive. And in COVID, they ramped up the COVID testing. And, so I'm not, saying that LabCorp doesn't do a really good job at what they do, but they really didn't know what to do with new knowledge that they generated in-house by acquisition of LipoScience. And so there was no marketing, no awareness creation. And basically LipoScience went invisible and is still largely invisible. Most of the testing is still done by the people that were interested in the testing, thanks to LipoScience's efforts. So these X number of analyzers that were produced 15 years ago are what LabCorp is using to produce this information and this more exciting.
And what's the life of these analyzers?
Good question, because nobody's ever. So the magnets themselves, these superconducting magnets, last a long time and don't degrade, but they're using PCs, 10-year-old PCs, and anyway, they're all the moving parts. So they're not going to last much longer. And this is what maybe I'm most concerned about and most interested in people hearing about, because what needs to happen for this to continue, this clinical translation to continue at LabCorp, but also ideally broaden to the rest of the world is for an IVD company to come in and basically acquire the liposcience technology, and there's a lot of patents, intellectual property associated with this, a lot of expertise that comes from in terms of service and keeping these machines functioning well. And you don't learn, I mean, we've done so many millions of tests, and you learn by doing. So what people don't know is that at some point in the future, maybe sooner rather than later, these Vantera analyzers, first generation, only generation, are going to cease to function. And it would be a real shame, especially with the things that we're going to talk about that are more exciting than LP-IR and, in my mind, LDL-P, et cetera. So there's an issue here. There's a problem, and hopefully it'll be addressed by an IVD company taking over. I've tried to make the case to big multinational IVD companies, but NMR is too exotic. I mean, I basically show them that this is a completely de-risked proposition because we've already gone through the regulatory hurdles. We've already made the analyzers. We already have the experience. So it's not like starting from scratch with something that you're unfamiliar with, technology you're unfamiliar with. But, you know, these big companies have a lot of inertia, and, you know, talking to the right people or having these big companies be entrepreneurial. So I think this is maybe, if it happens, it'll be possibly a smaller IVD company or a new startup IVD company, basically taking the torch that liposcience.
And has liposcience said that they would be willing to sell those assets, the IP?
It's LabCorp that owns all
Sorry,
these
that's
assets.
what I mean. Has
Yeah.
LabCorp said that they're willing to sell
Yes,
that IP?
they're, and I think they realize, well, yes, they're interested in licensing the patents. Most of the patents have to do with the assays,
Yep.
so LP-IR and MVX that we'll talk about. So absolutely. But who's going to license them if there's no machinery to produce the information? So
what is your estimate of the cost per machine now if you were going to make a Gen 2?
Well, so these machines cost on the order of $400,000 or $500,000. But the beauty of it is, of course, that they last a long time, which we've shown, but they have no consumables associated with the assay. So it costs just as much to do 10 assays a day as 1,000 assays a day. So in a high volume setting, these tests are very cheap. And what we talked about LDL-P, and the NMR lipoprofile was the report that gave people the LDL-P information. But that comes from this simple NMR spectrum that can then use to extract much more information than LDL-P. LP-IR, DRI is just part of the story. There's all these other things that we'll talk about later. So in terms of efficiency, analytic efficiency, you couldn't ask for anything better because, you know, if you want to use NMR to produce a lipid panel, and actually after telling you that NMR only measured particles and not cholesterol, the basic information is encapsulated in all these NMR signals. So you can actually feed NMR data to a machine learning algorithm, AI, and train it to produce accurate lipid panel and apoB information. So we published this 4 or 5 years ago that you can actually use the NMR spectrum to produce an extended lipid panel, apoB plus lipids, no incremental cost to a lipid panel. The apoB doesn't add cost. It more than doubles the cost of a lipid panel if you want to do it by chemistry and use regular reimbursement in the US. So, you know, this, so it's extremely analytically efficient and cost effective. The thing that people probably don't appreciate, and I didn't appreciate as a naive professor, I thought, well, surely this will be commercially attractive if it can cut the cost of doing these tests. The cost of these tests is so much smaller than the price that is charged for these, and the insurance pays for these tests, that cutting the cost in half of doing the analysis makes no difference whatsoever. So this is, you know, we'll maybe get into this later, because what is true is that NMR, a single scan, can tell you a heck of a lot more than just your cardiovascular risk, your inflammation level, your diabetes risk,
your overall mortality risk,
mortality
as we're about to discuss.
This all comes in the same assay, essentially.
Well, I can think of no better way to introduce the MVX assay. So I'll tee it up for you and then take away the story. So, by the way, I went to have my first MVX drawn. We've been doing it on our patients for about 4 months now, and I just haven't got around to doing a blood test on myself. So I went out to LabCorp 2.5 weeks ago because I wanted to have the results back when we were sitting here. And wouldn't you know it, Jim, they screwed up the assay. So I don't have it. They got everything else. Every other test we ordered, they got, but they butchered this one. So I don't have my own to talk about. But the MVX is a composite score that measures, if I recall, 6 things. So small HDL-P, GlycA, which we haven't introduced yet and we'll talk about, citrate, and the 3 branch chain amino acids. So leucine, isoleucine, and valine. So why don't you tell us the story of how you developed this score? And I'll just give the punchline so the listener knows why they should be paying attention. This score seems to have remarkable, when it's normalized to a 0 to 100
Right.
number, the higher the score, the worse it is. This score seems to have remarkable predictive value of all sorts of things we want to avoid, starting with death, cardiovascular death, liver disease. While the first study that I saw was done in a very, very high-risk group of catheterized patients, and it would be easy to dismiss that it was only valuable in that population, it's been demonstrated in healthy populations as well. So tell us about the score.
Yeah, so it's a really interesting story, and, one question that gets asked is, well, why did you think of measuring those things, or did you have some mechanistic reason for focusing on these things that ended up contributing to this MVX Metabolic Vulnerability Index score? And the answer is no, that's not how it happened, and I do wanna make this point because MVX and especially MVX raises more questions than answers right now. Okay, so you really would like to understand if it predicts mortality so well, why does it do that? Is it causal? Can we intervene? These are the things that really matter clinically. So it wasn't starting out with some idea that branched chain amino acids are really important mechanistically, even though they are. Um, This was because NMR analysis has given us a very efficient tool to measure baseline samples from studies that follow people over time, 10 years, 20 years, 30 years longer, to see what develops. And so you really would like the ultimate idea in a biomarker is that it predicts the future. You want to know not if it's related to cardiovascular disease, but is it related to getting cardiovascular disease in the future? And so we have availed ourselves of, over the years, of baseline samples from many very large clinical studies. You mentioned MESA, multi-ethnic study of atherosclerosis. That's a NIH-funded study that started in about 2000. It's had more than 20 years of follow-up now. We were asked to measure the baseline samples 15, 20 years ago for free. Now I work for a company that has to make some money, but I had enough freedom to be able to offer that test. Initially, I asked for money, but then they finally said, well, we just can't find the money for that, but we'd really like to have the information. So it was measured for free. Same thing from other very large studies. Women's health study, 26,000 women at baseline in a study that's been followed up for many, many years.
Framingham
Many clinical
Offspring.
trials, Framingham Offspring study, all sorts of intervention trials, Jupiter, et cetera. The diabetes prevention program. I would like to quickly go back to that just for 2 seconds because we didn't finish the thought of what the diabetes prevention program, even though it's not published, tell us. And the important thing that it told us was not just that LP-IR score goes down with lifestyle intervention and branched chain amino acids go down when which is all good thing, but that those things going down, the delta between where it started and where you got after the intervention, very powerfully predicts incident diabetes or the lessened diabetes risk. So that was sort of the missing link. If you really want to argue causality, you really want to show that lowering LP-IR translates to lower diabetes risk, and it does. It's quite powerful. It hasn't been published yet, in part because the primary author died recently, unfortunately, and so it will be eventually. All right, but that's one study. So we've gone out of our way over time to make it possible for people that didn't have funding to get NMR data on baseline samples for observational studies and intervention studies going forward. MESA has been particularly useful to us, 7,000 people, baseline NMR, and because we supplied the assay for free, the NIH has given us access to the information about who developed cancer, who developed cardiovascular disease, et cetera, dementia, et cetera, all sorts of outcomes. And so the beauty is that once we have taken the NMR spectrum and gotten from it what we initially wanted to get from it, let's say LDL-P, these spectra are sitting there in a computer, stored on a disk. And when we develop the wherewithal to extract new information from the NMR spectrum, we can go back literally in a couple hours to interrogate a very large clinical trial and get prospective information as to whether it's predicting a particular outcome. So back to MVX, that's exactly what we did in this cardiac catheterization study at Duke University. 7,000 people over a period of years recruited into this biorepository. When they came to the cath lab, when they came to the cardiologist with chest pain or some issue that qualified them to have coronary angiography done. And their blood was taken at baseline and it's stored at -80, where it's perfectly stable for NMR analysis. So we got a relationship with Duke to obtain those samples, do NMR analysis. And we found in published papers that small HDL particles were particularly powerful in relating to the likelihood somebody would die during the roughly 5 or 10 year follow-up of this study. And then there was another thing that we could measure by that time called GlycA, and we might as well talk about GlycA now. It's another signal in the NMR spectrum that's not where the signal is that we interrogate for LDL-P. And so for 10 or 15 years, we didn't care a whit about any of those other signals. But a funny thing happened with where the GlycA signal is. It was basically superimposed or in the way of another broad signal that we were trying to interrogate to learn about the fatty acid composition of somebody's plasma, how much mono, poly, and saturated fats were in the blood. And to interrogate that, this signal, this sharp signal, was on top of that and was getting in the way. So we basically worked out a way of quantifying how big that signal was so we could subtract it from the other signal. But that was perfectly good quantification information. So that signal, which I wouldn't have thought to do anything with, the person who's does all my epidemiologic analyses, Irina Shalarova is her name. We had the MESA data sitting there. We could go and very quickly use the software we had developed to measure this sharp signal. And she just said, well, does it relate to anything that happens in the future in MESA? Oh my gosh, it relates to all sorts of things, including mortality very, very strongly. So what's up with that signal? Well, it turns out, going to the literature, this often happens. 20 years ago, somebody published a paper saying that the signal was an inflammatory marker. It actually comes from the carbohydrate, the glycan decoration that's on a lot of proteins in the blood. And most of these proteins are so-called acute phase proteins that increase in concentration in inflammatory conditions. And so even though this signal was not telling us which acute phase proteins were contributing to it, it was a composite. And not only did it essentially quantify the most abundant 4 or 5 acute phase proteins that contributed to this signal. But this carbohydrate decoration, this glycan decoration, is used for all sorts of purposes, signaling of different types, et cetera. So there's very complex, there's people worry about the glycome. It's like the proteome and the genome. There's a glycome. I know nothing about any of this. But one thing that where we know where the signal comes from, and it comes from a particular sugars on this carbohydrate. And inflammatory conditions, more of this decoration is put on some of these proteins. So actually, this GlycA signal is reflecting not only the levels of these acute phase proteins, but how much glycan is on them, which is also connected to inflammation. So it turns out, rather miraculously, that how big this signal is a very useful measure of your steady state, of your systemic inflammation level. It's a very stable parameter because it's the integration of lots of different things. So rather than CRP that you typically measure clinically to assess inflammation, it's very volatile. It goes up and down day to day. So all clinical recommendations for the use of CRP information say that you should take the average of 2 or 3 different measurements. Nobody does that, but that's the recommendation to get around some of this biological variability. GlycA doesn't suffer from that problem. That's probably in large part the reason that when added to CRP in a prediction model, it typically assesses the outcome more strongly than CRP does. But CRP tends to independently add. So inflammation is a very complex thing. This is a very unspecific marker, but it's a very stable and useful clinically marker of systemic inflammation.
Does it include, do you think, or capture what we see in the various interleukins?
Yes, so it's correlated strongly with IL-6 and other interleukins. And these correlations, but that's all we know. I mean, yes. And you'd really like to be more specific. And if there's local inflammation as opposed to systemic inflammation, this is not going to tell you anything, okay? But what it does do is offer you a simple and very cheap, because it comes along for the ride with the other NMR information. If you quantify this GlycA signal, you have a very powerful marker of the things that systemic inflammation contributes to.
Now, using hs-CRP as an example, Jim, which, as you pointed out, is going to rise with inflammation. One of the things that clinically we pay attention to is how high is it? So if I see a brand new patient and their hs-CRP is 2 or 2.5, in many ways, that's more disconcerting to me than if it's 40. Because the 40 is so high that I know it's really in response to something acute. They're probably getting over a cold. Maybe they got a vaccine 4 days ago or something like that. Now, of course, that doesn't obviate the point you made, which is I still want to see longitudinal data. Like I can't assume the 2 is bad, because I could also be catching something on the way down or on the way up.
Could be 3 or 1, depending on the next day. Yeah.
But it's usually the case that when something is very, very high, it really speaks to acute inflammation, which is less pathologically concerning. These low simmering ones that I see, those are the ones that give me pause. Is the GlycA the same as that?
No, it's very different than that. So CRP levels can go up 1,000-fold on an infection. GlycA levels the response is much more muted.
Because it contains so much information in it, you think?
I can't really answer the because as well.
It's just the observation.
Just the observation. Yep. And so it's true that if somebody has an active infection and you're trying to relate the GlycA level to mortality in people that didn't have an infection, you're going to be misled by that. It'll be higher by 2-fold, not 1,000-fold. So it's not immune to those changes, but you wouldn't want it to be because, it's an inflammation marker.
Yep.
So in people with inflammatory diseases, rheumatoid arthritis, psoriasis, et cetera, GlycA levels are significantly elevated, and they are responsive to anti-inflammatory treatment, and so it has all the characteristics of a useful biomarker to assess not only things that that you would like to have some visibility to, like systemic inflammation. I think we're coming to understand that that's an awfully important contributor, even though we don't understand the
Yeah.
mechanistic fine points to so many things, including mortality risk. So anyway, this is just, I just wanted to tell you that the way that we discover these biomarkers is different than the way other people discover a lot of biomarkers. So it's more the top down. We have a very efficient way of doing the epidemiology. So we know already that these markers have a strong relationship to human health conditions. A lot of the work that's done starting from bottom up with a mechanistic idea and a particular enzyme that you might maybe want to target as a therapy, you have to then do animal models, and then you go up to humans, and then you have to do expensive trials, and then you typically measuring these things is not as easy as it is to measure these things by NMR. So it's a completely different approach to discovery, and it's sort of irrational discovery because you're basically using these large databases of population studies and then discovering things that you really didn't go after discovering in the first place.
So there are three components to the MVX. You've already talked about the lipoprotein one, which is the small HDLP. You've just explained the inflammatory one, which is GlycA. The third one is sort of the metabolic one, which has the citrate and the 3 BCAAs. So how did you come to figure those out?
So you're right. So we actually, with the Duke collaborators, there had been a paper published showing that GlycA, there was a GlycA paper predicting mortality. The interesting thing about this cath-gen population is they came to the cath lab because they had some presumed cardiac issue. They have, in the study that we did, for 5-year mortality, 17% of the people died in 5 years, and they were about mean age of 60 coming in. So that's a pretty high.
How many? 15%?
17.
17%.
17% mortality, 5 years in people that were not
Wow.
elderly. 3 or 4 times higher for sure than a regular population. So the presumption was that these are people that died of cardiac causes, but less than half of them died from cardiac issues. 60% died of cardiovascular causes.
Which is very interesting. So 60% of the 17% of people who were dead by 65 were non-cardiac deaths.
Causes, yeah. So anyway, the mortality was the most prevalent outcome. It wasn't a new myocardial infarction or a recurrent myocardial infarction. These people died. and so GlycA predicted it, small HDL particles predicted it. We might talk more about that. And then we simply looked at all the other things that we had learned to measure, and we had just kind of started this activity. So branched chain amino acids, isoleucine, leucine, and valine, ketone bodies, plasma protein. I mention those two things because when you look individually at those things, ketone bodies and plasma protein, they have significant associations with mortality. So why didn't we use those as part of the MVX composite biomarker? Because we were looking for things that contributed independently and additively to the other things that we've already talked about. So the inflammatory part, GlycA and small HDLP, we created a subscore called the Inflammatory Vulnerability Index, IVX. The other 4 seem to relate. So we discovered that these branched chain amino acids and citrate, independent of GlycA and small HDLP, added to the prediction of mortality. Then it was, okay, why? And so then we went to the literature. So we really approached.
And you're doing all of this inside of LabCorp. So LabCorp, at least still at this point in time, had the appetite for the R&D.
Really, yes, they paid our salary, but that was, we were sort of left alone in this little building to continue what we were doing at LipoScience. So thanks to LabCorp for not getting rid of everybody. So then it was going to literature, trying to figure out, does this make sense biologically that these things might be related to mortality? And that's where you come to the literature that very powerfully speaks to the great mortality risk that people with several acute diseases, especially kidney disease and dialysis patients, heart failure patients,
Anything with cachexia, I could see
anything with
increasing.
cachexia,
Yeah.
so does, sarcopenia, um, old people. Okay, so there's a lot of literature, especially in the kidney disease
Mhm.
literature, that describe this vulnerability as coming from a so-called malnutrition inflammation syndrome. And it's called many other things, protein energy wasting syndrome. So the cachexia, the wasting syndrome, is part of this, but inflammation is part of this. Inflammation is probably the context that allows these dysregulated metabolism situations to exist. So the fact that malnutrition inflammation syndrome, we had the inflammatory parts, we speculated, but the branched chain amino acids were related, and they were related in the opposite direction that branched chain amino acids are related to diabetes risk. So high branched chain amino acids speak to insulin resistance, obesity, diabetes risk. Low branched chain amino acid levels speak to mortality risk. We can talk more about, you know probably much more about why this makes sense in terms of mechanism, because it's partly related to mTOR signaling and the whole skeletal muscle
Yeah, turnover of amino acids
turnover
and
and
muscle protein
catabolism, et
synthesis.
cetera. Um, but it was satisfying to find this literature and to say, oh, maybe these are just better biomarkers of something that's already understood in the acute context, clinical context. But in the catch-in population, nobody had described this in a cardiac, uh, well, in a cardiovascular cohort. And then, so we said, well, this exists in spades apparently in this presumed cardiovascular cohort. But then we did subgroup analysis within this 7,000 people in the CathGen study, and we asked, does this MVX association with mortality exist equally strongly in men and women, in people with and without obesity, in people with and without diabetes, with and without heart failure, with and without a previous myocardial infarction, with or without coronary catheterization, occlusion of the coronary arteries, with and without kidney disease. And it's not affected by any of those things. It's equally strong, if not stronger, in people without the chronic disease versus those that are disease-free. So in fact, the strongest relationship of MVX to mortality, you mentioned how exquisitely strong it is.
I thought that the hazard ratios were bigger in the Cath study than in the MESA study of healthy people.
That's true. That's true. And the reason is that for whatever reason, if these people came to the cath lab and they were enriched in people who ultimately suffered from these wasting syndromes, okay? And the fact that you see the same prediction, if not as strong for sure, in people with absolutely no evidence of any chronic disease. In fact, the studies that are most recently published, and the most interesting one that I'll mention is one that's not yet published but is about to be submitted for publication, MVX in young people, 30-year-olds. Would we expect to see the relationship? And you do see the relationship, but it's weaker. And I didn't sort of finish that. So the two subparts of MVX are the IVX inflammation part, and the other four parameters brewed together to form MMX, Metabolic Malnutrition Index. It's kind of an arbitrary thing to talk about these two parts of MVX because it's known that there's synergy between these. It's a syndrome, it's interrelated, intertwined, but on the surface, at least, it looks like it might be useful to take a high MVX score, and it might be due more to inflammatory reasons than the metabolic malnutrition wasting reasons. In which case, different therapies might be better suited for that person rather than somebody with the same MVX score with a more malnutrition issue. So we thought it might be clinically useful. That's why we did that.
Are they both, I know the aggregate score is reported 0 to 100. Do the two subscores get reported that
Yes,
way as well?
same way.
Okay. So you could say, Mr. Smith is a 75, which is very high risk. But when I look at his aggregate score, his IVX is only 25, his MMX is 80.
Yeah,
This is the issue. It's the sarcopenia
yeah,
and the wasting that is really driving his risk. It's not so much inflammation in his
right.
case.
That's a possibility. I don't think that that possibility will ever be found to be that different. So usually these are more because it's a syndrome.
Got it.
And
Yeah,
so
the numbers I used are wrong,
yeah, yeah,
that's the
but
spirit of
that's the
what you
idea.
mean. Okay.
Absolutely, that's the idea. And it's really we've learned a lot since this 2023 first publication about MVX in this cardiac catheterization cohort. The important thing that we did there, I was advised that I really shouldn't try to publish this until we had replication, because these hazard ratios were so dramatically different for low and high MVX scores. So in that paper, we reported a completely independent cardiac cath population in Utah, Salt Lake City, and it replicated very well. And since then, we have been interested in seeing if it replicates in other disease populations. And as we referred to, what about people with no overt disease whatsoever, younger, older?
Well, let's talk a little bit about that. The one that just came out, of course, was the MASLD paper. Is that the one you wanted to chat about?
No, actually,
Oh,
we could, and it just so because these papers are coming out
they're just
now.
coming out at a geometric rate,
Yeah,
which is great. I
and
mean,
the
that's so
reason
exciting.
the reason is that we just have to go back to existing NMR data. So we're mining other people's costly studies. We're piggybacking on their work, their funding, and getting very quick gratification about whether MBX is good for this or that or the other thing.
Is there one in an intervention study? Because that would be the next step is, I mean, maybe you've already done it where you say, look, we've got a MVX at baseline, hot. We're going to treat you guys placebo, non-placebo.
Yeah,
Yeah,
that's
you know where I'm going.
absolutely that has to happen.
Okay.
It isn't going to happen if nobody knows about MVX. And the thing that has been a little disappointing to me is how little. I mean, nobody read that 2023 paper. I was very proud of that paper. I thought there was a lot of meat in that paper, and a lot of implications clinically and otherwise. Um, but but people read papers that are called to their attention, and this is part of the problem. If this was a liposcience, if we were at liposcience, we would be promoting awareness of this paper in meetings, et cetera. And this isn't happening at LabCorp. Okay, so but now this will help.
Yeah. I mean, there's going to be a
This
lot
will
of
help.
people that are
So
listening to us. So that
right,
yeah.
and so yes, we would. That's the next step. What will be published this year will be, I think, sufficient for anybody to see the replication of the phenomenology fairly quickly after that first paper in heart failure patients. We could show this. The other thing that was kind of nice about that heart failure population is they also had a lot of frailty information. A lot of these were older people with heart failure in Minnesota. And so they were able to calculate frailty scores and also biological age by, well, not in that study, but in another study of older people. So some of the other things that are talked about a lot about relating to longevity and so on were measured in these studies that we've been able to look at MVX in. And in terms of frailty, physical frailty, correlation, but fairly weak with MVX, about a 0.2 correlation coefficient. So it isn't like, you need to have physical frailty to see the MVX be high or vice versa. And in terms of mortality risk, frailty, physical frailty on top of MVX score adds considerably. But MVX very powerfully still in the presence of frailty score predicts mortality.
And is it always a 5-year look forward?
No, and in many studies, it's longer than that, in part because you want the statistical power from more people having the outcome.
But there's something powerful about the short window. I mean,
Oh,
in many ways, that's
absolutely.
actually a feature, not a bug, if you
Absolutely.
can offer that insight, because we
Absolutely.
don't have many short-term predictive biomarkers.
Absolutely. And actually, the one study that I was sort of confusing with the heart failure study is a study called EPIs, and it's a study of older people with lots of things being measured, including these biological age measures by chemistry assay, not the epigenetic flavors. And a couple years ago, I think it was 2022, they had NMR information, and then they had all this frailty information, and 186 different variables. And it was done by some epidemiologists in Minnesota using the most high-tech ways of trying to deduce whether the associations were causal or not. I'm not really sure that really, to me, demonstrated that. But they use methodology that purports to assess causal relations. And out of those 186 things that were looked at, small HDL particles were the most powerful at predicting 2-year mortality in these people.
What would be a blind spot? Where does it get fooled? We already gave one example, right? Which is if you're in the throes of a brutal infection, you're getting over a cold, that could artificially elevate, although not to the same extent as CRP, the GlycA, that could offset it. Have you seen other false positives, so to speak?
No, I mean, we haven't really looked in ways to possibly see those, because we've looked overall at the prediction in a population, and these people at baseline either have this, that, or the other
Yeah, so it
disease,
gets kind
or
of
they
canceled
don't.
out in the wash at the population level,
Right,
probably.
exactly.
Yeah.
The question of whether it's causal or whether, so there's two questions. One, is it modifiable? So let's just, I've been speaking to the intervening 3 years since the paper was published. We now have really good data, some coming very soon, in different disease populations, that this replicates and is seen. It doesn't matter who you are, this relates to mortality risk. I want to come back to this later because you said something earlier about how MVX remarkably relates to not just mortality, but diseases that produce mortality. So I want to quibble with that idea a bit later. But just to get back to the question of, are there interventions which lower MVX, and then could we do the study of that intervention to show that that's connected to a reduction in mortality risk?
Before you do that, Jim, I want to go back to the 30-year-olds because we didn't really finish the swing on that. So
No, we didn't.
can
But
you, are you able to talk about that, or is that not
I'm
published?
going to talk about it, and I'm not going to say the name of the study, but
Okay.
and the paper, I just, the draft of the paper is about to be submitted.
It's just hard for me to wrap my head around the
No,
fact that any biomarker in 30-year-olds could predict anything.
this is very true, and that's why this is so interesting and novel. So the paper that appeared a couple months ago was from Mesa. So we've been talking about Mesa, 60-year-old people at entry. They weeded out all the people in Mesa that had any self-reported or otherwise diseases, so restricted to healthy, and average age 60 or so. And MVX by quartile had this stepping stone relationship. Not as strong, the hazard ratios weren't as different as in CathGen, but very significant. So that was the first paper.
Do you recall in that study, Jim, what the difference was between the first and the fourth quartile in hazard ratio? We're you talking
So
about like a 1.6?
unadjusted, it was about, I might be they're confusing other studies, but adjusted, it was like 1.5 to 2.
Okay. And we'll link to every one of these studies
Yeah,
in the show notes.
yeah.
But basically, in otherwise healthy 60-year-olds, the difference between being in the worst quartile, 75 to 100 score, versus the bottom quartile, 0 to 25, would be about a 52.
No, that's per standard deviation. So it's actually greater than that. It's maybe
Ah,
2 to 3-fold greater.
by quartile. by top to
quartile.
bottom
Yeah,
quartile. Got it.
yeah,
Wow. Okay. So big difference.
yeah. So okay, so those are 60-year-olds. So these are people. So my idea about MVX, I mean, people die when they're older,
Yeah.
and so this thing MVX comes into play when you're older, and maybe MVX scores go up with age. MVX scores are virtually unassociated with age.
What?
Yes, unassociated with age. And the major proof of that is this 30-year-old study. So here we've got 3,000 plus people who were entered into the study between the ages of 25 and 30. So we have an NMR analysis that was done when the average age of these people was about 30.
And this has got to be 30, 40 years ago, because otherwise you wouldn't be able to do anything
This was
with this.
35 years ago.
Okay.
And there were blood samples taken at time intervals, more frequent than 5 years for the first few years, and then 5 years after. So we have NMR data at year 10, 15, 20, 25, 30. So we know how stable the MVX score is over time. That isn't actually reported in this particular paper, but it's very stable. But the really interesting thing is that the distribution of MVX scores when these people were 30 years old is just as wide, almost identical to the 60-year-old people. There are people with low scores and high scores. And as you said, this is 30 plus years follow-up. So this is definitely premature mortality we're talking about. We're not, and these are all people that at baseline also were excluded from having any pre-existing comorbidities. Okay, so there's not only young, but they're healthy young.
We need to just stay on this for a moment, Jim. This is so counterintuitive. I just want to make sure not a single listener is failing to appreciate what you are saying. So I'm going to repeat it back, and I want you to correct me, because there might be errors where I'm oversimplifying. 35 years ago, we had a whole bunch of people that were aged 25 to 30, and we excluded all the people that had known issues. So if you had type 1 diabetes, or you had some childhood cancer, or whatever else, we didn't include you. We really looked at boilerplate, healthy 25 to 30-year-olds. We draw their blood. Every 5 to 10 years, we draw their blood again, and we run the MVX assay on them. The first and most surprising potentially feature, certainly the first surprising feature when you're doing a bunch of MVX scores on healthy 30-year-olds, is that any of them had elevated levels, because the most obvious thing is MVX must at some level be a correlate with age, which is the single greatest predictor we have of mortality. And so big surprise number one is you could be 25 or 30 years old and have an MVX score of 75, which is very high.
The upper quartile, the average was about 50, 51 score. The bottom quartile was about 27. So that's the range. And there were
so the distribution looks a little different than it looks in a 65-year-old
but that distribution
population?
is identical to Mesa. I mean,
it is
identical.
Wow.
Identical.
And Mesa was in 65-year-olds.
Okay.
And then you're saying not only do we have this distribution that mirrors that of people 30 years older, as we followed these people for 35 years, it predicted mortality. I am not aware, I'd have to think, Jim, but I don't think I can imagine a biomarker outside of a very extreme state. So you mentioned FH. Okay, if I know that I have two 30-year-olds and one has FH and one doesn't, and the FH one is not treated, I can tell you with a very high certainty that person's going to be dead in 30 years.
Right.
This one will not, or very unlikely to. But outside of edge cases like that.
Well, that introduces the question, how did you get a higher or low MVX score when you're 30 years old? You didn't acquire it because of some vulnerability, disease vulnerability. You acquired it at birth. We don't know. We have to look now at younger people.
We look at Framingham and Framingham offspring and try to tie that together?
We have plenty of MVX data from studies where genomic information is available, epigenomic information is available. I mean, it's a great question. I mean, again, like I said, I've got questions more than answers, but it's really fascinating and novel and important, I think, for sure. And because of what we've just talked about, I want to go back to this issue of whether MVX has anything to do with whether you're likely to develop cardiovascular disease or diabetes or dementia or whatever. And what you will find already in the literature are papers that indicate or suggest that MVX does have those associations with the diseases, many diseases that cause mortality. But I think all of these are artifacts of the way the analysis was done. Because as you appreciate, almost all cardiovascular endpoint trials, as well as many other types of disease endpoint trials, cancer, whatever, kidney disease, they typically combine fatal and non-fatal events. So if you die of a heart attack as the first consequence of having cardiovascular disease, or if you have a myocardial infarction and survive it, these are grouped together in a composite endpoint called CVD. And when you look at cholesterol, it makes perfect sense because of the etiology, because of how the cholesterol is connected to cardiovascular disease and events mechanistically, that there's nothing wrong with using a composite endpoint. The etiology is the same. You get cardiovascular disease, you die from it. You get cancer, you die from it. So you want to have a biomarker that predicts whether you're going to get the disease, and then that automatically tells you what your risk is for dying of that. What this says is that maybe there is a separate influence on whether you're going to die from the cardiovascular disease or the cancer or or whatever. And that's your metabolic vulnerability, your metabolic frailty, if you will. Frailty, I like the idea of metabolic frailty because frailty connotes susceptibility to dying. And even though people with high MVX score, like these 30-year-olds who have high MVX score, you look at them, they don't look any different than the people with low MVX score. So you don't see the frailty. But metabolically, it's there. It's basically setting you up to be more susceptible to dying from whatever disease or event, old age, that is going to contribute to your death. So dying sooner versus later is what MVX seems to influence, as opposed to getting the diseases that, quote, cause this. I tried to say this in the paper, but it's becoming much more clear now, especially with these 30-year-olds, that this is something that has to do with dying, not getting the diseases that cause the death.
So listening to you say this gives me an idea for a study that I'd love to see you do, Jim. So I don't know how much time you spend in the oncology world, but I'm sure you're familiar with Keytruda. It's to my knowledge, Keytruda is the single best-selling drug of all time. And in many ways, it's been a miracle drug in oncology, the single most exciting development in cancer in the last 25 years. For folks unfamiliar with it, this is a checkpoint inhibitor. So people that have a PD-1 mutation that take this drug, regardless of what kind of cancer they have, this could be pancreatic adenocarcinoma, lethal cancer. If you have this mutation, this drug basically takes the brakes off the immune system, and your immune system eradicates the cancer. But here's the question. Why could you take two people that have the exact same PD-1 mutation, the exact same cancer by all intents and purposes, and you give them both Keytruda, and one of them responds and one of them doesn't? Like, we don't know. We do not understand what's happening at the immune level to understand why that's happening. It would be very interesting for me to understand, and using Keytruda as an example, but you could do this with any therapeutic intervention where mortality is very quick, right? And you could ask the question, does this become a prognostic indicator of not just mortality, but probability of success of an intervention?
Yes. Yeah, that's precisely what possibilities exist. When I first talked about this to people at Duke, the collaborators of the CathGen study, the people around the table, the first thing they said was, wow, this would be a great test for surgeons who are asked to operate on people who are frail or are less likely to survive the surgery or to benefit from the surgery. You'd like to be able to screen them for resilience somehow, but there are no biomarkers, good objective biomarkers to do that. Malnutrition, metabolic malnutrition, there are people, I've read papers where surgeons are suggesting that people really should avail themselves of these, interrogating whether somebody is sort of metabolically or physically frail, and has evidence of wasting. But if there's a metabolic component to that is accessible via MVX, it could be very useful. And this is one of probably all sorts of possible applications. You mentioned this paper that was just published 2 days ago on MASLD.
MASLD, yeah.
Okay.
The artist formerly known as NAFLD.
Formerly known as NAFLD. So liver disease. And the paper speaks very forthrightly about the possibility of using MVX to for entry into clinical trials.
Am I correct in remembering this paper, which I skimmed, so I'm ashamed to admit I didn't read the paper, but I could have sworn it said that MVX added predictive value to FibroScan in predicting subsequent fibrosis in the MASLD patients. Does that
I
ring
think
a
that's
bell?
true. I only skipped it as well.
Okay,
I was
it
not
just
a
came out,
co-author on
so
that paper.
yeah.
But, as you well understand, so many clinical trials are expensive and are not done. Many are not done because the events are too rare.
Yep.
And so you
Or
need a
too
huge
far away.
population or too far away. And so being able to juice up the likelihood of people dying, for example. So but mortality is probably the endpoint that people care most about, right? And so it has sort of in the hierarchy of events, it's people care more about dying than they do about getting an MI or getting diabetes or whatever. So anyway, there's all sorts of possibilities, but we're just at the beginning of the trail of answering the questions and I don't even know all the questions that could be posed, but this really is very fascinating. And the fact that it was discovered fairly serendipitously by interrogating these epidemiologic data sets, and then the relationships seem to make sense in terms of what's been published about the detailed, cell biological mechanisms, which I don't understand.
And it's an inexpensive test.
Well, it's basically free if you think about it. So I mean, this is what.
How many tubes of blood do you need to run it?
No, so you mentioned that you got your MVX score, and they probably drew an extra tube of blood for that. They don't need to do that. The same specimen, actually 150 microliters of plasma, produces the NMR spectrum that produces the NMR lipoprofile, produces glucose, produces LP-IR, produces GlycA, produces MVX. All of that comes from the same analysis. And when done in high volume settings, these are tests that really literally cost $1 or less. Okay, but this is the problem commercially, and this is the problem with our healthcare system and the way things are set up, that there's sort of no, there's almost a disincentive to provide analytically free information if you can't charge incrementally for it. And what you'd like to do if you're a company is charge a whole lot more for it. And then you have the tension between what you'd like to charge and what the insurance wants to pay for. And then convincing the insurance company that it's worth paying for is what keeps you from being successful commercially in, producing this test globally, broadly. I had this experience with LDL-P, tremendous resistance to paying. So, I think one way around that is to not try to pay paid incrementally for it, and just do something that. So the analogy is the comprehensive metabolic panel that you get done every time you go for. There's 14 things that are measured there. If you add up what the CMS reimbursement rate is for those 14, it comes to $60 and change. CMS pays $12 for that. And it's because these are all done at the same time. They have some, clinical reason to be done at the same time, and economies of scale make it efficient enough that you can make money and people aren't going to starve producing this test for getting paid $12 as much as they'd like to get paid a lot more. This is a situation just like that where the information is essentially free. And we made that point in the paper we wrote about the lipid panel, the extended lipid panel that includes apoB. I mean, we didn't really get to the apoB.
It was actually the last thing I wanted to get back to,
Yeah,
which was the discordance between apoB and LDL-P.
Let's get back to that, because the apoB story is the same as the LDL-P story. And the reason that I have partnered rather than competed against Alan Snyderman, who's the biggest proponent of apoB, is that it would be disingenuous to, say that one is really better than the other. I could make the case that the NMR analysis tells you LDL-P, but also TRLP, triglyceride-rich particles. Subspecies might be differentially related. There are people publishing papers that suggest that's true. So you could definitely be ahead of the game with more information than apoB provides. apoB is just a single measure of all the apoB on LDL and VLDL particles. But the challenge is convincing people that you should do something other than measure cholesterol. and so you need as many people in that fight as possible. So Alan and I are both telling the same story, and that's why we transitioned. I mean, I have advocated that we use NMR to produce apoB, and actually we got FDA clearance for the quality of the apoB information that comes from the NMR spectrum via the machine learning approach. So the idea was the extended lipid panel would have no analytic cost associated with adding apoB to a lipid panel. Now you have a better lipid panel. The way that Medicare reimbursement is set up now, apoB gets paid $20, lipid panel about $13. Last I looked, it might have changed a little. So that if you want to add apoB to make the lipid panel better, it's more than double the cost to the payers. The payers aren't going to want to do that.
And what's the CMS reimbursement on the NMR of lipids?
It's about $30 and change. And so that's for the NMR lipoprofile. The NMR lipoprofile comes with LP-IR.
Okay, yep.
Okay, we couldn't get that FDA cleared at the time, but you might know that a lot of laboratories can offer tests that are not FDA cleared through sort of a loophole the FDA has decided to exercise discretion about whether they will enforce this or not. So laboratory developed tests, LDTs, individual laboratories can develop their own test, go through get CLIA certification. So this is more laboratory certification for how well they perform the test. But the actual demonstration of the clinical utility of the test is something that FDA cares about, but CLIA doesn't care about. And so it's an easier path to offering commercially a test that doesn't have to go through FDA clearance. And so LP-IR was added to the NMR lipoprofile as an LDT, not part of what was cleared. LDL-P was cleared, but not without great difficulty. So anyway, a lot of the reason that NMR wasn't commercially successful has to do with what I just explained about the resistance of payers to pay any increment to what they're paying for now. And if you really need to demonstrate, what the path to getting insurance to pay is to get some advisory panels to some clinical guideline group to bless it. And and Alan Snyderman can speak to the difficulty of having apoB blessed by the cholesterol guidelines.
Although the European guidelines
The
have.
European guidelines and now the US guidelines are,
Yep.
getting, but it's just ridiculous. But part of it is because the guideline writers are trying to protect the payers, which that shouldn't be their job. They should be assessing the clinical utility only and let capitalism worry about the actual Medicare reimbursement cost for apoB, which was set many, many years ago, has nothing to do with what it costs to do these immunoassays on these modern analyzers. So again, there's this complete disconnect between what's charged and what's paid for and what it costs to measure. It's the same thing that drug companies, are defending the prices that they pay to support the research, et cetera. So you can make the argument that you need to stay in business, you need to make more money. But anyway, I think I succeeded more as a scientist than as an entrepreneur in what happened to liposcience, because we really had gotten quite far down the road of making NMR testing broadly available to the benefit of so many people internationally, and that just got tanked when it was purchased by a lab testing company instead of an IVD company. So I hope anybody listening who has
I don't know that door is closed indefinitely. I think
No, not at all.
I think that the MVX test offers a very compelling reason why another company might want to come along and purchase those assets, and especially given the prognostic utility of that test. So let's talk now about this edge case of CETP inhibition. And one of the first things that stood out to me looking at the Broadway and Brooklyn trials, which were the phase 3 trials of obicetrapib, were that the reductions in LDL-P and LDL-C were greater than the reductions in apoB, if memory serves correctly. What do you think is happening there?
I know what's happening. So the NMR analysis, first of all, was using an older algorithm than the one that we've been using for the last 5 years. But even in the older algorithm, the issue of whether NMR can reliably quantify these very abnormal HDL particles that are produced by CETP inhibition. So HDL cholesterol doubles or more than doubles, not because the number of HDL particles doubles. It's in fact, the number of HDL particles actually goes down a bit overall. So what happens with CETP inhibition is smaller particles are made into larger particles. So the number of small particles goes down, number of large particles goes up. The large particles contain 5 or 10 times more cholesterol per particle than the small ones. So HDL cholesterol goes way up, and HDL particle number does not. But the problem in terms of the analysis is that there's a natural, so again, we're taking advantage of NMR signals from the different size lipoproteins being detectable and differentiated from their neighbors, right? And so at the interface of small LDL, the LDL gets so small, and then the largest HDL is its nearest neighbor. And there's a decent gap between the diameters of those particles, so they don't get confused normally. But when you've got CETP inhibition creating human beings that don't exist naturally and have HDL cholesterol of 120, 30, 50, your HDL particles get perilously close to the size of small LDL particles. And now NMR has the possibility of confusing the two.
That's incredible, just given the size difference between these particles normally, like the apoB and the apoA1 particles. I thought they were like a mile apart on that spectra.
So the good news, though, is that when you have metabolic situations that cause you to have large HDL, you also have the LDL size distribution skewed to the large LDL. So there's fewer or no small LDL particles. So what you can get away with in these extreme cases where somebody has really large HDL, and the NMR can tell when you encounter that situation, that you basically take away from the deconvolution model the smallest LDL particles, so it doesn't have the opportunity to say this large HDL is partly small LDL.
Yeah.
Okay. So what happened with the algorithm that was used in that study is you didn't have the opportunity to have small LDL at all, even though some small LDL was probably there. And so you saw this big decrease in LDL-P, but not apoB, because the NMR model was not
Double count.
allowing you.
It just
So it's
counted.
really an artifact of the difficulty NMR has with this situation.
So is the implication that in this case obicetrapib produces a disproportionate reduction in cholesterol content of particles relative to number of particles?
I know you've talked about obicetrapib, and you and most people are very optimistic about the prospects of obicetrapib, despite CETP inhibition not panning out for many other drugs. And of course, these were all initially investigated because of the potential to create higher HDL cholesterol. And now we certainly know that HDL cholesterol is not the HDL biomarker of interest, and people were being fooled into thinking that would
Yeah.
have benefit. Part of the reason I think, this is pure speculation, but it comes from somewhere, that even in the face of the CETP inhibitors that came closest to being efficacious, 20, 30% LDL reduction, but no benefit. Maybe something bad was happening on the HDL side to counteract what was good happening on the LDL side. What was bad on the HDL side? You know, given the understanding now that just having a lot of large cholesterol-rich HDL particles doesn't put you ahead of the game in terms of cardiovascular risk. What we now know is that small HDL-P is powerfully related to mortality, all-cause mortality. So what I told you is true, especially with the most powerful CETP inhibitors. They reduce small HDL-P by 10 or 20%. If you ignore what's going on at HDL and you only look at what's happening with apoB and LDL, you think obicetrapib is a no-brainer, it's going to be positive. But what if people are actually being hurt, maybe in terms of mortality risk, by the small HDL-P going down if there is a causal relationship there? Don't know that there is yet. We haven't, proved that. There's biological plausibility because of the proteins that hang on to on small HDL particles, which is partly why we think it makes sense in terms of antioxidation, anti-inflammation, that small HDL particles might have this inverse association with mortality risk. So anyway.
But are you saying that you think that it's possible that, because again, we still don't have the hard outcome trial, but your thinking is that if the hard outcome trial it demonstrates utility, it might be, you're saying it could be just due to the reduction in small HDL-P more than the reduction in LDL.
I'm suggesting that people's predictions about how much efficacy there's going to be
could be wrong
could
if
be
they're
wrong.
based on
And
the LDL
it may still be that
reduction.
the trial overall is positive or positive enough to have the drug go forward. But the most dramatic demonstration of something bad happening while something good is happening, and the two counteracting each other, is if the trial doesn't succeed like the other ones succeeded. So
Yeah,
I'm
interesting.
just, we have to wait for the trial. And then if the trial doesn't succeed, then I'll say, yay, I was right. But it's pure speculation.
Well, very, very interesting. And I'll have to go back and look and see what the magnitude of the apoB reduction was. But I just remember that it was less than
It was less, but it's
but
still
it's still reduced.
very significant. And
But you're heartened by the fact that small HDL-P was decreased.
yeah, and we've actually reanalyzed that data set, with the more recent. We do a better job in differentiating large HDL from small LDL, and so those LDL-P results are much more in line with the apoB reductions than that paper indicated.
Well, Jim, this is such a fascinating space, and this is a discussion that has been long overdue. again, I don't think there's many people listening to us that haven't at least heard of, LDL-P, HDL-P. They might not know what liposcience is. They might not understand in vitro diagnostics and any of the other things that go around to it. Probably a lot of people are not familiar with MVX, but my hope is that that starts to change after this. Regardless of how you think you've fared as an entrepreneur, you've fared remarkably well as a scientist, and I think that's the most important thing, because without the scientific foundation, I don't think any of the entrepreneurial stuff matters. But we do typically want them to be aligned. But put it this way, at the risk of insulting an entrepreneur, I would argue that it's easier to find a good entrepreneur than it is to find a good scientist.
Yeah, that's true, that's sort of the frustration that the science is so solid, so much more solid than many startup companies, are investing in. But it at the end of the game, it's commercial, it's financial.
I suspect it's the sector, right? I suspect you wouldn't have this difficulty getting people interested if we were talking about therapeutics. I just think
Sure.
that the diagnostic space and the reimbursement environment in the United States is one that is not especially attractive
Right.
to investors. That's my suspicion as to the issue, and that's why the MVX, I think, offers more than just a diagnostic. If it could be paired to a therapy, if it has the ability to save enormous cost on the back end with respect to therapeutic selections, there are a few trials that need to be done to demonstrate that. But to me, that's the interesting area.
No, you're right, and that's what will make it successful commercially. My vision, though, that wasn't realized is how cool would it be to go to your yearly physical and get a lipid panel that had glucose, LP-IR, GlycA, MVX, at no incremental cost. In the rest of the world, not the US, where you have national health care, there is a premium put on how efficient a diagnostic is. And if you can get a lot of information for less work and money, that's worth something in the rest of the world. It's just, we tried to skin that cat in the US. So that it's, I haven't lost hope, but I really left LabCorp because I didn't want to beat my head against that wall any longer and wanted to spend my remaining years doing the science. So that's what I'm continuing to do.
Fantastic. Well, thank you, Jim, and thanks for taking the time to come out here today.
You bet.